In this video, I would like to introduce a very nice problem of Polish Mathematical Olympiad edition 2001-2002. Here is the following information. Determine all positive integers a, b, and c such that the numbers a squared plus 1 and b squared plus 1 are prime, and also this equation, which is this prime a squared plus 1 is multiplied by b squared plus 1 equals c squared plus number 1. Hold this equation, okay? Be careful, a squared plus 1 and b squared plus 1 are only prime numbers, but c squared plus 1 is not a prime. So I would be recommend to give the try to this problem. Prior get into the solution, go ahead, pause this video when you come back to see the full solution, okay? Now let's get started. Without loss of generality, we have this pair of the solutions, a and c and b is a solution, and also we have b and c and a is a solution because of the symmetry, okay? Because a and b are the symmetry, okay? You may ask why I'm putting this. I put this pair of the solutions on this form, acb, not abc. I will tell you that in a few minutes, okay? Let's set p equals e squared plus number 1 and q as a prime equals b squared plus number 1. I put this one on this form to make sure these numbers are the prime, okay? I'm going to break this one into many cases. I'm going to discuss the case when we have this prime and this prime are both even numbers, okay? So if p equals q equals e squared plus number 1 equals b squared plus number 1 equals number 2 as a even prime, okay? This one implies e equals b equals number 1 as a first case, okay? I'm going to replace this information into the original equation to see what's giving us, okay? So I'm going to replace this one. 2 is multiplied by 2 equals c squared plus number 1. It's equivalent 4 equals c squared plus number 1. By taking number 1 to the left, I will get c squared equals 3. This is impossible because we have this perfect square. Number 3 is not perfect square, which means both primes are not even prime, okay? This means the possibility to have both primes are even is impossible. You may have one is even prime, the other one is not even prime, which is odd prime. I'm going to see this one in next case, okay? If p equals e squared plus number 1 is an even prime, which equals 2, but q, which equals b squared plus number 1, is an odd prime, okay? I'm going to discuss this case. I'm simply going to replace e squared plus number 1 with number 2 into this equation to see what's the expression, okay? So I will have number 2 is multiplied by b squared plus number 1 equals c squared plus number 1, like this. By simplifying out this equation, so I will get 2b squared plus number 1 equals c squared. This one is telling us c is odd. To make sure if you find the solution of this equation, c is always odd, okay? I'm going to move over this 2b squared to the right side of this equation and leave number 1 to the left, which means I get c squared minus 2b squared equals number 1, okay? So I have ended with this following equation. What's this equation telling us? This equation exactly is a Peel's equation, okay? This one equivalent to x squared minus d y squared equals number 1. It's called Peel's equation. Okay, this is the special equation. If you have transferred your expression into this equation, that's mean you have Peel's equation. In the other words, we have many infinitely solutions for this equation. So now I'm going to determine the solutions. I'm going to factor out this equation. I will have c minus square root of 2 b factor c plus square root of 2 b equals number 1, okay? The solution for this equation, if you have x, y is a solution. In our case, we have c and B as a family pair of the solution, which exactly that I have written in the previous assumption. Okay, we are going to put our solutions in this order: A, C, B. Okay, remember we are fixing A, which equals 1, with A equals 1 because we have taken P as an even prime, which equals 2. In the other word, A equals 1. Okay, because 1 plus 1 is giving us 2. So the solutions that I'm going to have, which is A, C, and B, in this form. Okay, now I'm ready to solve this equation. So since we have a positive integers, we don't have to worry about the minus sign here. Okay, so which means this term equals 1 and this term equals 1. So now I'm going to find the first obvious solution, then build other solutions based on the first solutions that we are going to find. So the pair of the solutions which satisfy this equation is C equals 3 and B equals 2. Okay, if you are going to replace this one into this one, is given as number 1. Look, you have 3 squared, which is 9. This one is giving us 4 is multiplied by 2, which is 8. 9 minus 8, which equals 1. Okay, so this is the first obvious solution. Let's call it as C naught and B naught. Okay, like this. To make sure, in order to determine all other solutions, we are going to use the recursion here. So recursion, what's mean? If we have a solution, if we have a first solution for this equation, which means the solution that we are going to find and to raise it to the exponent n, whichever the value of n replaced is giving you a new solution. So other solution is going to be written on this form: C naught and B naught to the n equals, I'm going to replace this one with its value. I will have 3 plus square root of 2, number 2 here, okay, to the n. So this is the first solution. If I'm going to replace this one equivalent to n equals 1, if I'm replacing n equals 1, I'm going to extract these solutions. The solutions that we have is number 3 and number 2, which we have here. Okay, so if I'm going to find the second solution, I'm simply going to replace n with number 2. It's a very known equation. I'm not going to provide the proof now. I don't want to make this video long, so for next time we may have the separate video for the proof for this equation, Bell's equation. Okay, so if n equals 2, we will have a second solution, which is 3 plus 2 square root of 2 square. I'm going to distribute this one. If I'm going to distribute this one, is first term is given as 9 plus square of this one, which is 4, is multiplied by 2, which is 8. 8 plus 9, which is 17, plus 2 times this one, which is 6, is multiplied by 2, which is 12, square root of 2. So the second solution, which is 17 and 12. Okay, so this one is going to be, so I will have C1 equals 17 and B sub 1 equals 12. Okay, this is the second solution. If I'm going to replace this one into this one, it satisfies this equation. If you replace 17 square, which is maybe is 289, this one it will have B square, which is 144, is multiplied by 2, which is 288. 289 minus 288 is given as number 1. Okay, third solution, I'm simply going to replace, I'm going to have the same thing here, which is 3 plus 2 square root of 2 cubed. 3 plus 2 square root of 2 cubed. This one is given as 3 plus 2 square root of 2 square, is multiplied by 3 plus 2 square root of 2. So this one is exactly as this one that we found before. Okay, and it will be multiplied by this one. We will have 17 plus 12 square root of 2 is multiplied by 3 plus 2 square root of 2. If I'm going to distribute this one, we will find the following result, which is 99 plus 70 square root of 2. So I'm going to extract the solution from this one. C2 which is 99 and B2 which is 70. Okay, so as you replace the exponent with any value of n, you get a new solution. Okay, so we will have infinitely many solutions. Also, we are going to have a couple of these solutions due to the symmetry, because the a square plus 1 and b square plus 1 are playing the same role. So if you have if you give the value of a equals 1 and you find the value of b, which means also you can replace b with number 1, and the solution that you found for b is going to take a place as a. Okay, let's clean up this board and put those solutions on the side and continue solving our equation. Previously we were working on the second case and came up with this following infinitely many solutions for Peele's equation. So we found for the pair of this solution of type ACB, we found these solutions 132, 117, 12, 199, 70, and so on and so forth. Okay, for the symmetry reason, okay, so we found this pair of the solutions BCA, we found 231, 12, 17, 1, 70, 99, 1, and so on and so forth. So the general solution for the Peele's equation, to find a new solutions, we are going to use this expression. As you take in the n as a new value, you get a new solution. Okay, in this case it was a result when we have the first prime p equals this one as an even prime, with b squared plus number 1 was an odd prime. Now let's move on to the next case. If we have both prime are odd, okay, if b which equals a squared plus number 1 is an odd prime, and q which equals b squared plus number 1 also is an odd prime. Okay, if both are odd, we will have this product. This odd is multiplied by odd is giving us odd number on the right side of this equation. So we will have a squared plus number 1 factor b squared plus number 1 equals p is multiplied by q equals c squared plus number 1. Okay, since we know p is an odd prime and q is an odd prime, so this product is an odd, which means the right hand side of this equation is also odd. Okay, which means c must be even. I'm simply going to solve this equation by putting one of the term equals the whole term, which is c squared plus number 1, the other one equals number 1. Okay, by system of the equation, I will have p equals a squared plus number 1 equals c squared plus number 1, and q which equals b squared plus number 1 equals number 1. Okay, if you take a look carefully here, we're going to cancel out number 1 from left and right. This one is telling us b equals 0, which is impossible, because we have b as an odd, impossible b equals 0. Okay, which means we have no solutions if p and q are both odd. So I have done with this problem. If you have any question or suggestion, just put it in the comment section below. Don't forget to support us with your like and subscribe. Thank you for watching. We will see you next video. Bye.